by filling in this chart one more time just to recall what we did. Here you go. Can someone help me out? Sine of 90 degrees minus theta. It's cofunction. Yeah, no. Cosine of what? Of theta. Yeah. Good. Now our cofunction of cosine of 90 minus theta. Remember cofunction? It's just the co in front of one of them and just the base word in the other. No one remembers the cosine of 90? Yeah, John. Yep, just the sine of theta. Tangent of 90 minus theta. Yeah, thank you. Cotangent of theta. Wow, you are on a roll. I'm sorry. I will move faster just for you. Is that clear to everyone, this chart? This chart should make sense to you. You guys investigated it yesterday, that the sine and the cosine, the tangent and the cotangent, and the secant and the cosecant, those are cofunctions. If you have cofunctions and two angles that add to 90, they will be equivalent. They will evaluate to equivalent. Yeah. Oh. They give you information. So let's move forward to make sure so in the examples, they give you two pieces of information. Then they tell you to evaluate this. Now you know the sine of 30 degrees, but we're just using cofunctions, maybe reciprocal identities, to like utilize this information. It's not there for decoration. They want us to somehow use this information. So yesterday I think we did this one together, but I'll rewrite just these first two. Sine of 30 from our cofunctions chart, that's the same thing as cosine of 90 minus 30, right? Sine of theta, same thing as cosine of 90 minus theta. Cosine of 90 minus 30 is just cosine of 60. Cosine of 60 they gave us, and that's how you know you're right. If you get to a point and you're like, oh, well, they gave me that. So I think, Michael, in the book, they give you cosecant of theta, and it's equal to 3. And so that's how they get it as 3. It's not just like magic. Yeah, look at the book. Tell me if I'm wrong. Cosine of 30, that's the same as sine, its cofunction, of 90 minus 30. These are pretty straightforward. I think that you guys are rolling. I just want to make sure that you're understanding that you're not just saying, oh, I know cosine of 30. You're using what they gave you and some identity or equation that we've established. So sine of 90 minus 30 is sine of 60. Sine of 60, we're good because we know that, like, if you get something weird and they didn't give it to you, you know you're probably off track somewhere. Yes. Yeah. So sine of 60, we're given that's square root of 3 over 2. We had both of those done yesterday, correct? Yeah? All right, moving forward. How far did we get on this page? So we did the first two? Can I have the answer for this first one? 1/3. And that's because sine of theta is the same thing as 1 over cosecant. That's our reciprocal identity. And that's also, they gave us that cosecant of theta is equal to 3. So we just plug in 1 over cosecant of theta, that's 1 over 3. Cosine, I think we had to use another reciprocal identity, 1 over secant of theta, right? That's what that's equal to, which is just 1 over 3 squared to 2 over 4. If you clean all this up, you guys, we did it yesterday, correct? So I'm just going to write the final answer just to make sure everyone has it. It's 2 square roots of 3 over 3. That's the final answer you should get. You should have more work than that, obviously. But so these ones we didn't get to. Yes. Yeah. It's that straightforward. You just need to identify what to evaluate, what you're given, and how they're related. That's all you're doing. So I'm hearing, Michael, that you noticed that secant of 90 minus theta is equal to cosecant of theta, right? We know that from our chart, right above, on the top of the page. Cosecant of theta, they gave us, that's 3. You're done. That's all it is. Just identifying the relationship between the given and what you want to find. So can someone tell me cosecant of 90 minus theta? Yeah. Oh, yeah, you know what? You're right. Yep. Thank you. Copy error. Thank you. Cosecant of 90 minus theta, we're on part D. What is that equivalent to? Yeah, Jonathan. Yeah, that's the same thing as secant of theta. We know that from our chart. We know that from discovering cofunctions. Secant of theta, hey look, secant of theta. 3 square roots of 2 over 4. Done. That's all it is. So with the previous period, I asked them to take out their homework and do those 4, or at least re-look at them now that we've completed the example. So if you could take out your book and a piece of notebook paper, or what your homework is on from last night, because it should technically be done. We're just going over to make sure it's established. And I want you to try these 4 with us. All together, we will take a moment to do this, and we'll go over them together. All right, we are on 1.3 part 2, switching over from our homework. We took a little break to 1.3 part 2. Today we are going to learn about memorizing and understanding the development of basic trig identities. Just kind of establishing them. First thing I want you to do, there's 1, 2, and 3, warm up. 1 and 2, from memory. Do you see that? From memory. You're trying your very best to do this from memory because that's how it should be pretty soon, you know, if not already. So really take some time to think about that. And number 3, they're just asking you to write something that's equivalent to what's on the page. So just rewrite it in some way that is equal to. Go ahead. All right, I'm just going to fill in the 2 charts and you can check what you got with what I got. Make sure we're on the same page. Hopefully, everyone got this for their 2 charts. Should be coming kind of quickly now to us. I'm going to flip over to number 3. Can someone tell me how they got this expression to something different but equal? Yes. Oh, yeah, very interesting. A plus B quantity squared. That's different. That's a different way to write it. Anyone have anything different? Yeah. 2A plus 2B. So that's actually squared. It's not a 2 times A or 2 times B. It's A plus B quantity squared, all to the 2nd power. And so what we do with this is, I don't know if you guys remember this, FOIL. You should remember. First, outer, inner, last. So we multiply our first terms together, that's a squared. Our outer terms, a times b. Inner terms, b times a, or same thing as a times b because it's commutative, right? Associative. And last, b times b, or b squared. If you simplify that, there's two a times b's. So we can write it a squared plus 2ab plus b squared. That's how you would rewrite this if you were foiling. Does anyone know how you could rewrite b? Yes. A times a minus. Okay, I see what you did. A times a minus. Is that what you did? Okay. Creative. What about factoring? This can be factored. It's difference of two perfect squares. Does anyone remember that? We know the first term is something squared, the second term is something squared, and it's a subtraction. So you can do a plus b times a minus b. And you can check that with foiling again. The first is a squared, the outer is negative b times a, and the inner is positive b times a. Those cancel each other out, and you're left with your last as negative b squared, and that's why I get a squared minus b squared. The two middle terms cancel. That's equivalent to that. See what you do. Yeah, John. Yeah, we just distributed. Very good. A to the negative 1. Yeah, Michael. 1 over a. If we have a negative exponent, we move it down to the bottom if it's in the top, and vice versa. If it's in the bottom, you move it to the top. No negative exponents. We don't like that. All right, E, you kind of had to just be blunt with that one. Does anyone know how you rewrite that? To be the same, but look different. B plus A. It's different, right? Okay. That went well. Let's flip it on over. Whoa. A lot of stuff happening there. All right. Key point 1. Along with the co-functions, that chart you filled out in number 2 of the warm-up, there are 3 sets of identities that we must memorize. You must. Kind of like memorizing the unit circle and everything that's on it. It's memorizing, yeah, but if you understand it, it's way better. It's not as bad. It's easier. It just makes life easier. So let's see what we got here. So we got co-functions. We have reciprocal identities. That was Monday's lesson. That was the last set of notes from the purple packet where we learned about reciprocal identities. Number 2, quotient identities. We never officially called them this, but you will recognize them once we write them. Quotient identities. And lastly, Pythagorean identities. Whoa, big word. We will establish these 3 today and tomorrow. We will go through how they came about. You know, math isn't magic. There's a reason that it is the way it is. So we're going to show you why. I swear it's not magic. All right. So this is something that maybe you should try and write down without looking, but refer to it because, like I said earlier, we do need to memorize these. These are just the, if you're looking at that triangle that we always draw in the first quadrant, they're just saying opposite over hypotenuse, y over radius is what that R is standing for. So if you want to take a moment to fill that out, or try and even do it without looking. If you have a question. So you said one thing that was accurate, which is 1 over sine is equal to cosecant. That's right. We have that right here. 1 over sine is equal to cosecant. But how can sine be equal to 1 over sine? That's the relationship we established on Monday between them. That sine is, we know sine is y over the hypotenuse, y over the radius. But we also established that that is also equivalent, sine is equivalent to 1 over cosecant. And it obviously works the same way. If we flipped sine over 1 in 1 over cosecant, that's how you get this. So if you can memorize like half, you just flip them all over, you got the other half. Moving on. Are we good? We're good. Moving on. Quotient identities. Didn't I tell you recognize them? It's just writing tangent and cotangent in terms of sine and cosine. It's not anything special. You wrote tangent and cotangent in the reciprocal identities, but this is just using sine and cosine. Once again, you know tangent and cotangent are reciprocals of one another. So if you remember that tangent is sine over cosine, you should remember that if you just flip it, that's cotangent. And these last ones, Pythagorean identities, they look kind of weird. They got some squares in them. That's sine. You read the sine squared of theta plus cosine squared of theta equals 1. This is 1 plus cotangent squared theta equals cosecant squared theta. And last 1 plus tangent squared theta equals secant squared theta. This will establish definitely today. Well, maybe most of it, and then the other two will be tomorrow. Yes. Is cotangent, repeat it. Is cotangent equal to secant over cosecant? Cosecant. Yes. Yes. Because you're just replacing cotangent is cosine over sine. And so you're putting in the reciprocal identities. I see what you did there. Yes. Very interesting way to look at that. Yeah, a lot of other things can come from this. It's not just what I'm giving you. All right. Very cool. Example 1. Flipping on over. Show how sine squared of theta plus cosine squared of theta is equal to 1. Is derived from the Pythagorean theorem. Whoa. Do we remember what that is? Yep. A squared plus b squared equals c squared. That'd probably be a good place to start, considering they say they want us to derive this from this. So obviously we're starting with the Pythagorean theorem. Okay, so we're starting with the Pythagorean theorem, but it's in the context of the unit circle, so we should probably draw ourselves one of those. We're drawing a triangle inside the unit circle. Why? Because doesn't the Pythagorean theorem apply to right triangles, right? That's the only place this works, is on right triangles. So we're going to draw on a right triangle like we've been doing in a lot of our unit circles when we're establishing things. And we're going to try and relate our equation over there, our Pythagorean theorem, to this triangle inside of our unit circle. So if that's the case, what do A and B represent on any given right triangle? The legs. Good. So this could be A and B. Doesn't matter. I could have switched them. They're legs. They're both the same. Okay. So that means this is point A comma B. Remember? This is our x distance. This is our y distance. Do we agree? Point A comma. Okay, so what does C represent? Someone. The radius. Yeah. And what's the radius in the unit circle? 1. So we know this is 1. So now can we rewrite that using what we've labeled over here. So how would I write the Pythagorean theorem with this specific triangle? Yeah, equals 1. 1 squared, but that's also just 1. Very good. Awesome. We are on our way. I have a question. How could you write a number as a fraction? Like if I said 2 and I wanted it to be 2 over something, what would I write it as? 2 over 1. It's there, we just don't write it. So we could rewrite a and b as a over 1 and b over 1. Do we agree? Yeah? Equals 1. Okay. Everyone freeze. We need to somehow get sine and cosine into this because we have a's and b's, we have 1's. How do we get sine and cosine involved? Do we see maybe this kind of looks like a trig ratio answer? What is a over 1 according to our triangle here? So if this is theta, right? What's a over 1 equal to? Theta of what is adjacent over hypotenuse, right? That's a over 1. It's adjacent over hypotenuse. No one remembers what adjacent over hypotenuse, what trig function? Cosine, yes. So we can replace a over 1 with cosine of that theta. But it's all squared. You have to remember that. That's why we can put that squared there, is because this whole thing was squared. The cosine was squared, so that's why we can do that. It's not like I'm just throwing that 2 in there for good measure. All right, so now b over 1, what is that showing us? Theta, some trig function of theta is b over 1, opposite over hypotenuse. Yes. Sine, yeah, but sine, so this is sine, so that means this is sine squared. We have to square it because our b over 1 is being squared. Equals 1. Do you see how this is the adjacent over hypotenuse, this is opposite over hypotenuse, and we related it all back to those trig functions we learned like in that right triangle trig packet 3 weeks ago, 2 weeks ago. Whoa, yeah, full circle. So you could write this, obviously, you know that this is equivalent to sine squared theta plus cosine squared theta equals 1, right? That's how do I don't know how to do it. I wanted to write in that a over 1 is adjacent over hypotenuse and b over 1 is opposite over hypotenuse. I think that'd be a good note so you remember where this is coming from, why a over 1 squared is magically cosine of theta squared. Like, where is that coming from? So make sure you note to yourself how that's happening, because you guys talked me through it. Does this make sense to anyone? Is there any step here that doesn't make sense? We went from the Pythagorean theorem to the specific triangle in the unit circle with radius 1. Then we rewrote it just differently and realized, hey, that's a relationship we know with this triangle, within this triangle. And that's how we saw it. Does that make sense to everyone? That's super important how it comes about, because, hey, that makes it a lot easier for you guys to remember, right? That's not memorizing, that's understanding. So I'm going to stop our notes there because we're going to do example 2A and B tomorrow. Your assignment for tonight is fix or maybe even completely redo that bookwork. And also that the sheet that you picked up when you walked in, does everyone have one of those? It looks like little flashcards. what I want you to do is fill out the back. The backs are empty, so take time right now. Right now, what I want you to do is fill out the back of those. They're little flashcards for you to practice. So I want you to take some time, fill that out. And if you have time, I'd like to see you quiz each other, because those are things that are going to need to come about pretty easily. So go ahead and get started on filling out your flashcards.